All right, today we're going to focus on something called the ideal gas law. The ideal gas law is probably the most important gas law of all the gas laws, and it's the most often used gas law on the AP chemistry exam for those of you that plan on taking AP chemistry in the following years to come. Now, with an ideal gas law, we make two big assumptions. And the first is we treat all gases the same. If every gas is an ideal gas, it doesn't matter if the gas is hydrogen, if it's helium, or if it's methane. It doesn't matter what the gas is. If it's ideal, we can treat the problem exactly the same no matter what the gas is because they're all behaving ideally. We make two big assumptions about an ideal gas law. And when we make these two assumptions, if they do behave this way, then again, it doesn't matter if the sample is helium, hydrogen, or methane, or any other gas that may be. Okay? So the first assumption we make that makes it an ideal gas is the first is that the gas particles are so small, and because they are so far apart from each other, the gas particles take up no space. Therefore, if I've got a container that's a 1 liter container and a gas is inside of it, we assume that the volume that the gas can spread throughout is 1 liter. In actuality, the volume is actually the 1 liter minus the space that the gas particles take up themselves. So the volume would be less than 1 liter in actuality. But we make the assumption that the particles are a point source, and because they have no space themselves, that the volume is truly the volume of the container. So it's an assumption that we make. Now, what gases are best at following this assumption? You're right, the smaller ones. Hydrogen is the smallest gas that there is, and it follows the ideal gas law the best. As the gas gets larger and larger, it does not follow this first approximation as well, and therefore when we use the ideal gas law, the gases that are bigger will not follow the gas law. So the numbers that we get from it, from the equation, the numerical value we get from it, will not be as close as it will be if it's something like hydrogen or helium, the smaller gases. The second assumption that we make is that the gas particles do not attract or repel each other. Therefore, the gas particles have no IMFs. Now we know the gaseous state has got the least IMFs associated with it. They still do, however, have IMFs, and when you have two gas particles that do come close to each other in a moment in time, they will interact with each other, but that gas law says that they have no interactions with each other. Therefore, we treat them like two independent point sources that just are not affected by each other whenever they come close to each other. Again, which gases follow this assumption better? Gases that have very low IMFs. So we're looking here for any gas that is a nonpolar gas. Nonpolar gases or noble gases. These gases have very low polarities. The only type of IMF they have is dispersion forces, and even those tend to be very weak. So if you have a nonpolar gas, those gases will follow the ideal gas law much better than polar gases. So these are type of multiple choice questions that were on the test for this unit. If we meet again later in the year and we take this test on this unit, that's the type of question you can expect to see. So the ideal gas law is PV equals nRT. P again stands for pressure, V stands for volume. Now the one thing with the ideal gas law is the volume must be in liters. In the other gas laws that you've done homework on, hopefully for, you can have it in milliliters. Just make sure both sides of the equation have milliliters, or you solve for milliliters. But in the ideal gas law, the volume must be in liters. The pressure can be in any pressure units. It can be in atmospheres, kilopascals, torr, millimeters of mercury, any gas units. The temperature, as normal for any gas law, must be in Kelvin. And we get a couple other new letters that we have not seen in any other introductory gas laws. The ideal gas law has an N in it, and the N stands for the moles of the gas. How many moles of gas are in our sample of our test or question? The R is called the ideal gas constant. And it is what causes a proportionality to become an equality. Whenever we take and add a constant to an expression that we know is a proportionality, it causes that proportionality value symbol to become an equal sign. And this constant was derived through mathematical interpretations from scientists way back several hundred years ago. And the R, as you can see, this table shows all the different potential R values that you could use. These are found on your green sheet. And the key there is to look at the units. If you'll notice, all of the units for volume are all liters. This is why the volume must be in liters. The temperature is in Kelvin, must be in Kelvin. And obviously the end is moles, moles of gas. The unit that is unique is the pressure unit. This is the only reason why we have different R values. If we are doing a problem which there's atmospheres, we must use the 0.0821 R constant in it. If we are in kilopascals, we must use the R constant of 8.314. So instead of having to always convert between the pressure units and always get them into atmospheres, we just have to use the appropriate R that matches up to the pressure units. It becomes a simple plug and chug into the equation, and we solve for the missing variable. So pick the right R and make sure your units of volume, temperature, and mole quantities are in the appropriate ones. Okay, let's do a few example problems on this. The first problem says calculate the number of moles, so we're going to calculate or solve for N. The volume is in 3 liters. We'll notice that it's in liters, so we're good. We don't do any conversions. The temperature is in Kelvin. Again, we don't do any conversions. And the pressure is in atmospheres. Because our pressure is in atmospheres, we have to use the R that's got, the atmospheres in it. So we want to pick the one that's 0.0821, the one that has atmospheres in it for our constant. That's the thing you got to make sure, pick the right R based on what units of pressure we're using. So the ideal gas law only has one set of conditions. So whenever you're reading a problem, if they only give you one pressure, one volume, one temperature, you're going to use the ideal gas law. If they have multiple, if they change the pressures or the volumes or temperatures, if they're making changes to them, then we're going to use the combined gas law from last lecture. PV over T equals PV over T. All right, so plug and chug here. We're going to solve for N. So the pressure is 1.5 atmospheres. The volume is 3 liters. The moles, we don't know. We're going to solve for N. The R is 0.0821. Okay. And that has units of, let me see here for a second, atmospheres, liters per mole Kelvin. And the temperature is 300 Kelvin. So we've plugged in all the numbers. We can see the only variable we don't know is N. So we just go ahead and solve for N. And to solve for N, we would divide these numbers over. And compute and solve. And I got a value of 0.183 moles. So this would tell me now the number of moles of gas that was in this sample. All right, so go ahead and do problem 2. And if you want to pause the lecture now and try it, please do. But I'll go ahead and now solve it, and then you can see if you get it right. So the first thing we see is a gram sample of nitrogen. Nitrogen is diatomic, very important. If you did the problem and screwed up, that might have been the thing that you did wrong. First thing is, we'll notice that mass is not in the ideal gas law, but we should be able to remember that we can always convert mass into moles. So 1 mole of N2 weighs 28.02 grams. Again, nitrogen is diatomic. So we get 0.0250 moles of nitrogen. Standard temperature for any gas, standard temperature is 273 Kelvin and 150 kilopascals. We are now in units of kilopascals, so the R that I want to use is the 8.31 kilopascals R constant. We are asked to find for the volume, so that's my question mark is the volume, so I'm going to now use the ideal gas law. And oftentimes, if I want to solve for a specific variable, I'll a lot of times solve for the V ahead of time before I do my plug and chug. So now I'll plug in my mole quantity, my R this time is going to be 8.31 because we're in kilopascals. Our temperature is 273 Kelvin. And the pressure is 150 kilopascals. If we look at unit analysis, the kilopascals will cancel, the moles will cancel, the kelvins will cancel. We're going to be left with a value in liters. And as I said, the ideal gas law, you will always get liters for volume or must plug in liters for volume. So, solving that, plugging in the calculator, 0.378 liters is the answer. Okay, hopefully that's what you got. If you tried the problem, then matched it up. But if you didn't, you can probably see where you went wrong. Okay, problem 3. A sample of oxygen gas has a volume of 7.84 centimeters cubed. And again, centimeters cubed is the same thing as a milliliter. So 7.84 milliliters at a pressure of 71.8 kilopascals and a temperature of 25 degrees Celsius. What will the volume of the gas be if the pressure is changed to 101 kilopascals and the temperature is changed? If you see multiple temperatures and multiple pressures, multiple volumes, this is not the ideal gas law. The ideal gas law is looking at one set of pressure, temperature, volume conditions. Therefore, when we see changes to both pressure, volume, and temperature, this problem is looking back at yesterday's lecture, which is the combined gas law. You must be able to seamlessly float from one gas law to another gas law. In this problem, we're going to need to use the combined gas law and not the ideal gas law because we're not worried about the mole quantity of the gas. So in this problem, we'll just plug in. Now, because this is the combined gas law, we do not have to worry about having it in liters. We can keep it in milliliters. So we'll put the first set of conditions. Again, the temperature must be in Kelvin, so 25 degrees Celsius is 298 Kelvin. We'll have that set equal to the other side. We don't know the volume. Plug in the new pressure. And 273 Kelvin is 0 degrees Celsius. We never plug Celsius into any gas law. Solving for the volume using the combined gas law. Now again, since my volume unit on the left was in milliliters, we will get an answer in milliliters. 5.11 milliliters is what I got. Okay. Last problem. Use the ideal gas law to verify the volume of 1 mole of gas at STP. Well, we know from the last couple lectures that this is looking at Avogadro's molar volume. Any gas at STP, if we consume it's an ideal gas, we should get a volume of 22.4 liters per every 1 mole. They're asking us to use the ideal gas law to go ahead and see if we can verify that value. So since 22.4 liters is a volume quantity, again, I'm going to solve this equation for volume. I'm going to plug and chug. So the volume would be, the mole quantity, 1 mole. We'll use the R of 0.0821 because we'll be in atmospheres. STP, standard temperature, is 273 K. Standard pressure is 1 atmosphere. Again, the moles cancel, the kelvins cancel, the atmosphere cancel, we're left with volume. If we go ahead and punch these numbers in, what do we get for the volume? Guess what? We get 22.4 liters. What we have done, and this is how they determined the R constant, they were able to create the proportionality, and because 22.4 is always given, they plugged 22.4 in to the ideal gas law, and they solved for the constant, and that's where they got the 0.0821 from. So the ideal gas law was utilized for the derivation of the ideal gas constant. Okay, let's turn the page into the next page. All right, on this page, what we're going to do is simply take the ideal gas law. The most common form of the ideal gas law is PV equals nRT. But what we can do is do some derivation work using some other equations, do some substitutions to create different forms of the ideal gas law that might be more important to use in different situations. The first one is molar mass. It's not very easy to calculate or know the moles of the gas in a problem often. It's much easier to know the molar mass of the gas than its mole quantity. Well, molar mass is given as big M in these mathematical equations for gas laws. And molar mass can be calculated by knowing the mass of the gas and its mole quantities. Because we see N is in the molar mass equation, we could do a substitution into the ideal gas law. We do that by first taking this molar mass equation and solving it for N. So if I move the N over and move the M over, the moles of a gas could be calculated by simply taking the mass of the gas sample and dividing it by its molar mass. I can now substitute this in for the value of N. And what I get now is this form of the gas law. PV equals MRT divided by big M. If we move the big M over, we get this form of the ideal gas law, which now incorporates the mass of the gas sample and the molar mass of it. Rearranging this equation and solving for big M, we get this equation. The molar mass of a gas is equal to the mass of the gas sample, the ideal gas constant, the temperature divided by the pressure and volume of it. This is a gas law that we use in the molar mass of the gas lab. It's one of the labs that we did or do in this unit. And after the next couple weeks, after spring break next week, we'll take a look at how we're going to move forward in this class. And one of those might be, how am I going to have you guys maybe do this lab, but actually do it in some type of virtual setting. But figuring out the molar mass of the gas by taking some measurements of the sample. So in the homework for this ideal gas law problems, you might have a problem that involves molar mass. And if it involves molar mass, you might use this form of the ideal gas law instead of PV equals nRT. One last thing we can look at is density. Sometimes the density of gas might be very useful. And density is given by mass divided by volume. You'll notice in this gas law right up here, MPV equals mass RT. M and V are both in this form of the ideal gas law. If I rearrange and move the V over, I get M over V. And therefore I can, instead of measuring the mass and volume independently, I can actually just get them out of the equation and replace it with density. So the molar mass of a gas times the pressure of the gas equals the density of the gas times the ideal gas constant times the temperature. This is another form of the ideal gas law that you might find to be very useful to do any of the homework problems for today. If the problem involves any type of density in the problem, that is the form of the ideal gas law. So now you have 3 different forms of the ideal gas law that you might find very useful in doing these problems very easily. Pick the right one that has the variables that you see. It's much like Algebra 1, and solve for the missing variable. Rearranging this equation for D, as this acquires over here, D equals molar mass times pressure divided by the constant and temperature. So these are different variations of the gas law you might use for the homework. So let's do an example problem here now, number 3. It says, what is the molar mass, so that's going to be big M, of a pure gas that has a density of 1.6, and we know the standard temperature and pressure, STP. All right, so we're going to use the ideal gas law that involves or has density in it. All right, so I'm going to pick that bottom one. MP equals DRT. We're going to solve this for M. We want to know the molar mass, so I'm going to move the P over. So the molar mass is given as DRT divided by big P. And now it simply becomes plug and chug. The density is 1.40. We're going to go ahead and use 0.0821 because we're going to look at the atmospheres. Standard temperature is 273 Kelvin. And standard pressure is 1 atmosphere. Because I'm going to use atmospheres, that's why I'm going to use the 0.0821. Okay, go ahead, do the mathematical work. and we get a molar mass of 31.4 grams per mole. Okay, I didn't show all the unit analysis in the problem, but if you go through, plug all the units, cancel out, you should be left with units of grams per mole. Okay? Lastly, a conceptual understanding. We've been talking about ideal gases. If all gases are treated as ideal gases, that means it doesn't matter what the gas is, the problem would be exactly the same. So if I had 1 mole of helium and did a gas law problem with it versus 1 mole of carbon dioxide, I could do the same gas law in plug in, doesn't matter if it's helium or carbon dioxide, I would get the same answer. So if we treat all gases as ideal, it doesn't matter what the gas is to do the problem. So again, what are the two assumptions we're making about the ideal gas? In an ideal gas, how much space do the particles take up? In the ideal gas law, what do we assume? We assume they take up 0 space. In real life, however, they take up a little space. And that little space is very tough to calculate, and that's usually what involves calculus in order to figure that number out. So we will never have to worry about the real gas law. We'll only look at ideal gas law just because of its simplicity. Ideal gases, we assume, what about the IMFs? Again, yes, we assume 0 IMFs in the ideal gas. Real life, there's a small amount of IMFs. Because they're vastly separated from each other, much distance between the particles, usually, again, small gases are more ideal gases. Okay? And so we assume small again. So because of this, we make these assumptions. The ideal gas law is very easy. All we have to do is plug into PV equals nRT. And we don't have to worry about these little bit of spaces that are being taken up and the little bit of IMFs that they have with each other. If you get into college chemistry, eventually you'll actually work with what's called the van der Waals equation, which will mathematically be able to figure out what these small little quantities are, and then you get a much better value using the forms of these gas laws. So again, what are some assumptions we're making about the gases? The molecules of the ideal gas are dimensionless points. They take up no space. The molecules in ideal gas are constantly moving, and they're moving in straight lines until they bounce off of something. The molecules hitting the walls of the container is where we get pressure. The average kinetic energy of an ideal gas is proportional to its absolute temperature. So the kinetic energy is directly related to its temperature, which we've talked about in the last unit. As the temperature goes up, the molecules move faster. If the molecules move faster, they have more kinetic energy. Again, kinetic energy is 1/2 m velocity squared. Not volume, but velocity. If the molecules are moving faster, they have a higher kinetic energy. So kinetic energy and temperature are directly related. Molecules, when they collide with each other, their collisions are elastic. What does elastic mean? For those who take physics, elastic means that when they hit each other, they bounce off of each other. They don't stick to each other. So they collide with each other, they bounce off, and when they bounce off just like two pool balls when you play pool. They strike each other, they bounce off, and they travel off into a different 3D direction. The molecules of ideal gas exert no attractive or repulsive force with each other. They have no IMFs of an approximation. So these are the assumptions we make about all gases if we treat them as an ideal gas. Okay? Now, which gases behave the most ideally? That's a key fundamental conceptual question. That's a question that was asked or will be asked on this test in this unit. Which gases are the best at following these approximations? We want to pick gases that are the smallest gases. And what do we use to help us assume the smallest gases? We will use molar mass. The gases that have the smallest molar masses will be the most ideal gases. They will follow the ideal gas law the best. Therefore, the number that we get from the calculation of the gas law will be very close to what it actually is in real life. Also, we want to pick gases that have very low IMFs. And the gases that have very low IMFs are going to be small, nonpolar, or noble gases. We want to pick the smallest nonpolar gases or the smallest noble gases. And those gases tend to have very low IMFs, and they also follow the ideal gas law approximation the best. So you might have some conceptual questions on the homework for today. And when you do those problems, those are things you want to look for. These gases will be better than other gases. So for example, if you had hydrogen or carbon dioxide, which gas would follow the ideal gas law better? Hydrogen would. It's smaller than carbon dioxide. It's going to follow the ideal gas law better. Those are the type of questions to be prepared to answer. One last thing is conditions. Which conditions favor ideal gas law? Colder temperatures or hotter temperatures? Colder temperatures, the molecules are moving slower. And if they're moving slower, when they come close to each other, they stay closer to each other longer, and therefore they have more chance to interact. That is not ideal. So here it says real gases deviate. Deviate means which conditions are the worst at following the ideal gas law. Colder conditions are bad for gases because the molecules are moving slower. They also tend to condense and they get closer to each other, and if they're closer to each other, they interact with each other more often, and that's not a good thing when we assume that they have no IMFs with each other. Pressures. What's bad? High pressures are bad. Higher pressures usually mean the volume is smaller, the molecules get closer together, and now the particles are taking up more space than the container size, and they also, again, are closer to each other, they're interacting more often, and that's bad with the approximations. So when we have cold temperatures and high pressures, the gases do not follow the ideal gas law very well. And these conditions are getting closer and closer to the gas actually becoming a liquid. And that should make sense. If it's getting closer to being a liquid, it's not going to follow a gas law very well because it's not a gas. So in these labs that we did for this class, we would want to try to look at the conditions of the gas. Are we working with high temperatures and low pressures? If we are, we will assume that the lab is going to give us very good values. If not, we can expect our values are not going to do very well with the ideal gas law. Okay? So these are some things to consider to look at when we look at ideal gases. So again, an ideal gas doesn't matter what the gas is. If we treat it ideally, any gas can be used in a problem exactly the same, and it makes the calculations quite easy. So go ahead, give the homework a try. I believe it's on page 11. I think it's just one page. Do these problems. Again, the answers are on Canvas, and give it a try. If you have any questions, let me know through either a Canvas notification or send me an email my way. Good luck, and thanks again for listening.